All right, so you want to like really get how things work, or,
Yeah,
like the real core stuff, the fundamentals of the tech that's kind of shaping everything around us without getting lost in the weeds.
for sure.
And that is exactly what we're going to try to do today. We're diving deep, deep into Cassandra.
Deep.
Like way down.
Down to the bottom.
Yeah, Cassandra. Now, this is a piece of technology that's it's a foundational piece that powers a lot of what we do online, a lot of what happens. And our guide today, our Sherpa, if you will,
Okay.
is this fascinating article from way back in 2008.
Wow, 8.
Written by one of the very people who actually created it at Meta back when it was still Facebook. So it's like this rare behind-the-scenes glimpse into where it all began.
That's super cool. I mean, to see how these things actually came about, from the people who were there.
Absolutely, yeah. It's like a time capsule in a way.
Yeah.
So our mission today, right?
Yeah.
We want to understand why they built Cassandra in the first place.
Makes sense.
Like, what problem were they even trying to solve? And then how did they go about doing that? What are the core design choices, the principles that make it tick?
Right.
And I guess ultimately, why does this even matter today?
Yeah, why should we care?
Yeah, why should we care about this old thing?
Old thing.
This thing from the past? Well, because it's kind of still around.
It's still kicking.
Yeah.
It's all over the place.
It really is. And understanding how it works at its core gives us a lot of insight into the broader world of data infrastructure, all those systems that are kind of the backbone of the internet.
I see.
And of course, maybe you need to get up to speed quickly.
Yeah.
Maybe for work or, for a discussion or just out of curiosity. This deep dive is designed to give you that solid understanding of a key technology quickly and efficiently.
All right, I'm in.
Okay, let's jump in. So the article starts off describing this really significant problem that Facebook was wrestling with at the time, and it was all about inbox search.
Inbox search.
Yeah. Just think about the scale of Facebook back then, and I'm sure it's grown tremendously, but even then it was huge. Millions and millions of users sending messages, like constantly.
Right.
That's a mind-boggling amount of data.
It is.
And they had to make all of that searchable.
Yeah.
Every message instantly for every single user.
So it wasn't just about storing the data.
No.
They had to make it accessible.
Exactly. And make it accessible fast.
Right.
Because everyone expects search results to be like, boom.
Instantaneous. Yeah.
Right there. And the article really hammers this home. It talks about the immense volume of these messages, how fast the data was growing, and the fact that they had these very strict service level agreements.
SLAs.
Yeah.
Those are the promises, right?
Yeah, basically promises about how fast and how reliable the search had to be, and they had to meet them.
Right.
Now, it sounds like the data storage solutions that were available at the time, the off-the-shelf stuff,
Yeah.
it just wasn't up to the task.
It couldn't handle it.
No, it just couldn't scale to that level. And maybe even if it could, maybe it was prohibitively expensive or something.
I see. So they needed a new approach.
Yeah, they needed something different.
Something custom built.
And the interesting thing is, and I think this is where the article starts to get really exciting, is that the people who created Cassandra, they weren't just thinking about fixing inbox search. They were thinking bigger. They had a vision for something more broadly applicable. They wanted to build a storage infrastructure, a foundation that could tackle many similar large-scale data problems.
Oh, wow. So they were looking ahead.
Yeah, way ahead. Like it's almost like they had this crystal ball, they could see where things were going. And the article mentions, this is another really cool detail, that Cassandra actually came out of a hackathon.
A hackathon? Really?
Yeah. It was like Prashant Malik and Avinash Lakshman, these two engineers, they just kind of got together.
Got their hands dirty.
Yeah. And just started hacking away. And what emerged was Cassandra.
Wow. So this super important technology, it started in this really organic grassroots kind of way.
Yeah. It's testament to the power of like practical engineering, being driven by actual needs.
For sure. So they built Cassandra, and it's a distributed storage system, right?
Yeah. So what does that actually mean?
That's a good question. It means that instead of storing all your data in one giant machine, you spread it out across many smaller machines, many servers.
Yeah.
And these servers, they work together, they communicate with each other to manage all that data as if it were one big system.
I see. So is that just to handle the volume?
It's partly about volume, but it's also about reliability.
Okay.
When you have a system that might involve hundreds or even thousands of servers, potentially spread across different data centers, you have to expect that individual servers will fail.
Right.
Like things break.
Yeah, things break.
Hard drives crash, servers overheat, networks go down. It happens all the time. And so Cassandra is designed from the ground up to handle these failures gracefully. It's what we call fault tolerant.
Okay, fault tolerant. So it can keep working even when parts of it are broken.
Exactly. And the article emphasizes that this is crucial, not just for the storage system itself, but also for the applications and services that depend on it. If your storage system goes down, everything built on top of it crumbles.
Makes sense.
So this ability to manage persistent state, to keep the data safe and accessible even in the face of these failures, that's a key innovation of Cassandra. And it's a big part of why it's able to scale so effectively.
Okay. So we have scalability,
Yes.
high performance,
Yes.
high availability,
Keep going.
broad applicability. Like those are the key goals that Cassandra achieves.
They nailed it.
Yeah, pretty impressive. Now, the article is careful to point out that while Cassandra might look and feel a bit like a traditional database, it doesn't actually implement a full relational data model.
Right.
It has a different kind of data model, one that's arguably simpler and gives users more flexibility in how they structure their data.
More freedom.
Yeah, exactly. And I think that's something that's worth diving into a bit deeper.
For sure.
So the basic unit in Cassandra, the kind of the atomic element, if you will, is the row.
The row.
Yeah. And each row is identified by a unique key.
Okay.
And this key can be any string, and it can be basically as long as you want. It has no size limit.
Wow, that's a lot of flexibility.
Yeah, it really is. Now, a Cassandra instance has one table, and that table is composed of one or more column families.
Column families.
Yeah, it's kind of like categories of data within your table.
I see.
So you decide what column families you need when you set up the Cassandra cluster. You give them names, and that defines the basic structure of your data.
Okay.
And the article mentions that there's no practical limit to how many column families you can have.
Right.
But once you define them, they're fixed. You can't just change them on the fly.
Okay.
Now, within these column families, there are two key structures, columns and supercolumns.
Columns and supercolumns.
Yeah, it sounds a bit intimidating, but it's actually pretty straightforward. Both of these can be created dynamically.
Dynamically.
Yeah, so you don't have to define them in advance. You can just add them as you go.
Okay.
And you can have as many of them as you need. No limits. So let's start with columns. A column, it's really simple. It has a name, a value, and a timestamp.
Okay.
And that timestamp, it's user-defined.
User-defined.
Yeah, so you can basically control how you track time within your data.
I see.
Now, the interesting thing about columns is that the number of columns you have per key, it can vary,
Very.
like significantly. So one row might have 1,000 columns.
Wow.
Another row might just have a few, and they're all within the same column family.
So it's very flexible.
Super flexible. And this is where it really starts to differ from a traditional relational database.
Right.
In a relational database, you typically have a fixed set of columns for every row in a table.
Yeah, that's the way it usually works.
But Cassandra is more freeform. It lets you store whatever you need, however you need to store it.
Okay.
Now, supercolumns, they add another layer of nesting.
Nesting.
Yeah, so a supercolumn, it has a name, and then associated with that name is basically an unlimited number of regular columns.
I see. So it's like a column within a column.
Yeah, kind of, or like a subgroup of columns within a row.
Yeah.
And these columns within the supercolumn, they inherit all the same flexibility as regular columns. They can be created dynamically. There's no limit on the number. It's all very free-flowing.
Okay, so it's columns all the way down.
Pretty much, yeah.
Yeah.
And this data model, it's really designed for situations where you might not know all the pieces of information you need to store up front,
Right.
or where the structure of your data might change over time.
That makes sense. So it's about adaptability.
Yeah, exactly. Now, the next big question is how Cassandra actually manages all this data across its many servers.
Yeah. How does it all work together?
Right. And more importantly, how does it make sure that the data is reliable and accessible even when parts of the system fail, which, as we said, is bound to happen?
Right. Because things break.
Things break. So the article talks about using something called consistent hashing.
Consistent hashing. I've heard of that.
Yeah. It's a technique that's commonly used in distributed systems to spread data evenly across multiple nodes. But then they added this other twist, which is an order-preserving hash function.
An order-preserving hash function. That sounds interesting.
Yeah, so consistent hashing, it kind of ensures that your data is distributed nicely, but it doesn't really care about the order of the data.
Okay.
But the order preserving hash function, it does care about order. It makes sure that data that is logically close together, like say data from a particular time range, it ends up stored on servers that are close together.
I see.
And this turns out to be really important for certain types of queries,
Okay.
like range scans.
Range scans, yeah.
Yeah, where you want to retrieve data within a specific range of values. And the article specifically calls this out. They say that they implemented this order-preserving hash function to enable efficient range scans for later data analysis.
So they were thinking ahead.
Yeah, they were really thinking about how the data would be used, not just how it would be stored.
Smart.
Now, to manage the cluster itself, like how all the individual servers know about each other and whether they're healthy or not, Cassandra uses a gossip-style membership protocol.
Gossip style.
Yeah, it's like a social network for servers.
Okay.
Each server periodically chats with a few other random servers, and they exchange little bits of information.
Like, hey, how you doing?
Yeah, basically. And have you seen this other server lately?
Tease it up.
Yeah. And through this gossip, they maintain a shared understanding of who's in the cluster and who's not.
Okay.
It's very decentralized. No single server is in charge of keeping track of everyone.
So it's more resilient.
Exactly. If one server goes down, the others can still keep gossiping.
That's pretty clever.
Now, for high availability, Cassandra relies on replication.
Replication.
Yeah. So they make copies of the data and store them in different data centers.
So if one data center goes offline.
The others can still serve the data.
Okay.
And this is where the concept of eventual consistency comes into play.
Eventual consistency. That's a big one.
Yeah, it's a key idea in distributed systems. So what it means is that when you request data from Cassandra, you'll get the most up-to-date version that's available. But because data is being copied around in the background, there might be brief periods where the different replicas are not perfectly in sync.
Okay.
But the system is designed to resolve these inconsistencies over time.
So eventually, they all catch up.
Exactly. And this trade-off, this acceptance of temporary inconsistencies, it's what allows Cassandra to be so fast and so available.
It's like prioritizing speed over perfect accuracy in the moment.
Yeah, it's a pragmatic choice. Now, another important aspect of Cassandra is its incremental scalability.
Incremental scalability.
Yeah, basically, it means that you can easily add more servers to your cluster to handle more data and more traffic. And these new servers, they automatically bootstrap themselves.
Bootstrap.
Yeah, they pull in the data they need from the existing servers, and they start taking on a share of the workload. It's all very smooth and seamless.
So you can scale up your system without any downtime and disruption.
Yeah, pretty much. And this ability to scale out on demand is another reason why Cassandra has been so successful. So let's talk about the first major application of Cassandra, Facebook's inbox search.
Yeah. How did it perform in the real world?
Well, according to the article, it was handling terabytes of indexed data across a significant cluster back in 2008.
Terabytes. That's a lot of data, even by today's standards.
Yeah, it was massive. And more importantly, the system was performing well enough to meet those strict SLA requirements they had.
So it was fast and reliable.
Yeah, it was doing its job. And the success really validated the core architectural decisions they had made with Cassandra.
Right. They had proof that it worked.
Exactly. And that paved the way for other teams within Facebook to start using Cassandra for their own data storage needs.
So it spread within Facebook.
Yeah, it started to gain traction. And here's something else that's really interesting.
Okay.
Even by August of 2008, which was just a short time after its initial development, a beta version of Cassandra had already been open sourced.
Open sourced. So they released the code to the public.
Yeah, and that really speaks to the value that they saw in Cassandra and their desire for wider adoption and contribution from the community.
They wanted to share it with the world.
Yeah, they wanted to make it a shared resource. And the authors of the article, they're very clear that building a system like this, it's an ongoing process.
Yeah, it's not like you just build it and then you're done.
No, it's constantly evolving. They talk about this continuous cycle of building core features and then adding more advanced functionalities.
It's iterative.
Yeah. And they end the article with this call to action. They're looking for talented engineers who are interested in solving these hard distributed systems problems.
Right.
Problems that affect millions of users. It's a great way to end the article. It really captures the excitement and the challenge of working on something like Cassandra.
Yeah, it's inspiring in a way.
So listener, if you've made it this far, congratulations. You've just completed a deep dive into the early history of Cassandra.
You've earned your badge.
You have. And here are the key takeaways. We learned about Cassandra's origin story, how it was born out of this very real need to handle massive amounts of data at Facebook. We explored its fundamental design principles, its focus on distribution, reliability, and eventual consistency. And we looked at its flexible data model, which is very different from what you'd find in a traditional relational database.
That's a whole different way of thinking about data.
It is. And now, here's a question for you to ponder. How do these core design choices of Cassandra, its distributed nature, its embrace of eventual consistency, how do those compare and contrast with the way traditional relational databases are built and how they function? What are the trade-offs involved in each approach?
That's a good one.
Yeah, think about it. When would a system like Cassandra be the perfect tool for the job, and when would it fall short?
It's all about choosing the right tool for the right job.
Absolutely. And we hope that by exploring the origins and the design of Cassandra, you've gained a better understanding of the forces that have shaped modern data infrastructure, the challenges and the solutions that have led us to where we are today.
It's all connected.
It really is. And on that note, we'll leave you to ponder.
Until next time.
Until next time, thanks for joining us.